This is lesson 1 of chapter 2 for AP College Physics. We mentioned in the last chapter the fact that this word dimension can have multiple meanings. Typically, we live and do our primary physics in 4 dimensions. One of those dimensions is a dimension of time. The other 3 dimensions are spatial, length, width, and height. There could very well be other dimensions. Certainly we have mathematical descriptions of other dimensions. It's hard to know whether they are real or not just because you can describe them mathematically. Some of the modern theories coming out of quantum mechanics and trying to understand various aspects of quantum theory invoke maybe 11 dimensions. I remember in my college physics and calculus differential equation classes that we were working in multiple dimensions as well. Not that I fully grasped what that meant. In any case, I'd like to mention a little bit about a couple of words here. The first word, prehistoric. That's a rather misleading term because as long as there are things going on the planet, ever since it was first came into being, there is history. Excuse me. Now, whether or not there was somebody to record that history is another thing. We should also say that a history does not have to be necessarily written down to be called history. You can have an oral history long before there is a written history. Some people have commented on the fact that there are some examples of written history before the time that Moses wrote the first 5 books of the Bible under the inspiration of the Holy Spirit. That does not mean that the first 5 books of the Bible came out of or were derived from the other written histories. What's important, since all written histories originally were oral, that means spoken, is how accurately was that spoken history passed down from generation to generation. And certainly when you read Scripture, you see how absolutely essential it was for the people of the Old Testament to accurately transmit God's revelation orally from generation to generation. Their very existence depended upon that. Their very relationship with their God depended upon that. So the question is not which group of people wrote down their history first. The question is which group of people wrote down their history most accurately. Because as we all know, stories can get embellished over time. Now, another term is this word mastery. The mastery of motion. And this is an example of something that human beings have always done, and that is to try to master something, to gain control or dominion over it. And that, of course, flows straight out of Genesis chapter 1, where we are told to have dominion, to have rule over God's creation. And, of course, this dominion and rule has nothing to do with being dictatorial or despotic. It has everything to do with being wise and careful stewards of something that has been entrusted to us by the one who made it. So that word mastery is an important word. Now we have 3 other vocabulary terms: dynamics, kinematics, and mechanics. Kinematics is a broader term that describes not just motion, but the causes of that motion. So dynamics, which is what chapter 2 is about, is a subset of kinematics, which we'll get to in later chapters when we start talking about forces and mass and energy. This term mechanics is a little bit more generic and has to basically do with things that are moving and colliding, and sort of a general everyday conversation incorporating dynamics and kinematics. Not terribly well defined, at least in this book. Now we have the idea that this has been going back for many, many, many years. Sumeria, or the country Sumer, is actually south central Iraq. It's where the Tigris and Euphrates rivers begin to come together and eventually flow into the Persian Gulf. It is also the region of the world where many people believe that perhaps the original Garden of Eden used to be located. In any case, that goes back approximately 5,000 to 6,000 years ago. Sumeria, it's one of the earliest civilizations that we have some archaeological information about. Egypt, on the other hand, goes back several thousand years. Maybe the pyramids were built around 2500 BC, and this is about 500 years before the time of Abraham. And Moses would have come about 1500 years BC, or about 1,000 years after the pyramids were built. It'd be kind of interesting to wonder if when the children of Israel were enslaved in Egypt, if they were aware of or had chances to visit or even perhaps had to do some maintenance of the pyramids. So this study goes back a long time. Now we come to a little bit more recent time, 2,300 years before today, not before Christ, and we get to the Greeks. And even before the time of the Greeks, even before the time of Christ, the Greeks were studying these kinds of things. They were studying motions, and they were studying particularly the motions of the heavens. If you think about why people have had such fascination with the movement of the moon, the movement of the sun, the movement of the stars, and the movement of the irregular stars, which we call planets, a lot of that fascination had to do with the fact that many people groups associated these objects way out in what we call space with various gods. Not only that, but your well-being depended upon the sun shining, for example. And you use this as a way of marking time so that you would know when to plant, perhaps, or when to harvest, or when to expect there to be a certain kind of weather, like winter or summer. And, of course, the earliest models were geocentric. Geo refers to the Earth. Centric means the idea was that the Earth was at the center of the solar system. It's a very logical conclusion because we're sitting here on the Earth and things appear from our perspective to go around us. And so this was the Ptolemaic perception, just a century plus before Christ, that the Earth was at the center of the solar system. However, we should point out that that was not a view held by everybody. In 250 BC, Aristarchus actually had a solar system in which the Earth rotated on its axis and revolved around the sun, which we now know today to be correct. The idea, first of all, that the Earth is spherical goes way back before the time of Christ. The mythology that around Christopher Columbus, that everybody thought the Earth was flat, and so if Christopher Columbus tried to sail across the Atlantic to find a shortcut to India, that he would sail off the end of the Earth, that is all a mythological idea, a fictional idea developed by an American author named Washington Irving, who lived about 200 years ago. He wrote about Rip Van Winkle and Sleepy Hollow. He also wrote a fictional account of the travels of Columbus. And he had a beef with the Catholic Church at the time, so he created this narrative that Columbus was a man of science, and he was battling the entrenched religious views of the day who believed that the earth was flat. And even today, sometimes Christians are called flat earthers. That is entirely fictional. Christopher Columbus, first of all, was a Christian. And number two, it was the academics, which was often conflated with many of the theologians who had adopted Greek philosophies that Christopher Columbus had to battle against. In fact, the academics and the theologians believed the earth was much, much larger than Christopher Columbus thought it was in terms of being a sphere. And so they had every reason to think that Christopher Columbus, since he thought the Earth was too small of a sphere, would run out of food and water. And he almost did. We move a little farther into history, and now we're talking about 500 years ago or so. And here we have Nicholas Copernicus, another Christian, with Catholic ideas. In fact, it was the Catholic Church throughout much of the Middle Ages that did the astronomy, that kind of laid the foundation for science as we practice it today to take place. Science really took off as a result of the Reformation, which I've talked about before and we'll talk about again sometime this year. But he went back and revisited this idea of Aristarchus and had what we call the heliocentric model, helio being a Greek word for the sun. Helium, the element number 2, was first found on the sun before it was found on the earth. And his model was interesting to people. They didn't see any problems with the geocentric model. They needed to be persuaded. And eventually that happened with Galileo. Now there are mythologies surrounding both Copernicus and Galileo as being men of science who were battling the entrenched and anti-scientific views of the religious people of the day. That is, again, entirely fictional. Both Copernicus and Galileo were Christians, though Galileo didn't have the greatest personal character. He could have used some sanctification. And he was pretty sarcastic in some of his writing about the Pope, which got him into hot water with the Pope. But in any case, Galileo gave much greater evidence that the Earth went around the sun and not the other way around. When he used a telescope, he did not invent it, but when he used the telescope, he found blemishes on the sun. And he also found that Jupiter had satellites, and both of these ideas would be contrary to the Greek perception of the solar system, where everything had to be spheres, and the sun, of course, could not have any blemishes. And the fact that Venus had phases could only be explained, really, that Venus was going around the sun from our perspective and not going around the Earth. By the way, Galileo did run into trouble with the Pope, but that was only because he was making fun of the Pope, and he was pointing out that the Pope at the time was involved in hiring an awful lot of his own family members, nepotism, for important positions, and the Pope decided he needed to take a hard line here to gain some credibility back. But the idea that Galileo was ever persecuted is totally fictional. He lived on a pretty posh estate in the Rome area, even though he was confined to that villa. All right, enough of the history. Let's do some quick overview of stuff that you learned in first year physics. Displacement, we sometimes represent that by the letter D, sometimes we represent it by the letter S, sometimes in the X direction by the letter X, and the Y direction by the letter Y. All of these can be displacement. You start off in one place, and now you're in another place with respect to something in the background. We're going to talk about, of course, velocity and acceleration as well. So in order to know whether or not something is moved, you need to have a frame of reference. And since we're sitting on the Earth, if I were standing in front of you and were to drop something, that thing that I dropped would appear to move, because since we're on the Earth, we feel like we're stationary. The Earth is our frame of reference. The wall in the back of the room is our frame of reference. And so the object appears to move with respect to that wall or with respect to us. However, if you were an ant or a bug on the pen that was falling, you would assume that the rest of everything else out there, what we would call the Earth and the room and you and me, was what was actually moving. So you need a frame of reference. And there are some great videos online, and hopefully I'll put them on Canvas if I haven't already done so, so that you can see these videos about frames of reference. Very, very important. Later on, when we get to Einstein's theories of relativity, frame of reference becomes extremely important. And we begin to realize that, technically speaking, there is no absolute frame of reference in the universe against which everything else can be considered to be moving. Now, this is an interesting picture. If you were looking at this picture right here, you'd have no idea, first of all, what it is, and second of all, how big it is. This is the Valles Marineris, a huge canyon or valley on the surface of Mars. You look at picture B, and you can see that it stretches across the what would be the width of the United States about 3/4 of the way. That's about the length of this canyon from one spot to the next is about 2,500 miles, and or about 5,000 kilometers. And we should also mention that the width here is quite wide. The width would be about 120 miles, 200 kilometers, which is about the distance from St. Louis to Columbia, Missouri. But what's really remarkable is its depth. It's really, really deep. If you ever go to the Grand Canyon, I've been there 3 times now, from the North Rim, you're 5,000 feet up. From the South Rim, you're 4,000 feet up. But the depth of this canyon is about 23,000 feet. That's over 4 miles deep, 7 kilometers. So this is a huge chasm on the surface of Mars, and it would be a good question as to what in the world caused that. All right, so displacement is simply defined as a difference in 2 positions. Notice that we use the triple symbol right here to mean defined as. The letter I is initial, the letter F is final. And so when we talk about your change in position as being X final minus X initial, notice we normally do final minus initial. It has nothing to do with how you got from one point to the other. You could have gone in a circuitous fashion back and forth, or you could have made a beeline from one spot to the other. But based upon where you started and where you ended up, your net displacement would be the same. We already talked about vectors in Chapter 1, and we represent these vectors with an arrow over the top to designate that they are vectors. Your book goes to the additional trouble of making it bold. Pretty much when we do our homework and when I write up my tests and so forth, kind of ignore the arrow all the time for vectors, because I'm going to assume that you know the difference between a scalar and a vector. You know what quantities are vectors and what quantities can't be vectors, like mass and time. Time, by the way, is unidirectional. Velocity, you're familiar with that. Velocity is distance divided by time in a certain direction. If you don't specify the direction, it's simply called a speed. You can talk about your average speed or your instantaneous speed at any given moment. Our units are going to be meters per second primarily. Part of the MKS system that we will be using, where distance is in meters, mass is in kilograms, this is kilograms there, and time is going to be in seconds, meters per second. Sometimes it will be convenient to use other units. All right. Notice that distance has a different precise mathematical meaning based on differences in the coordinates between the initial and final points. For example, if I talk about going in a straight line from St. Louis, let's say, to Los Angeles, on a flat map, I can draw a straight line, but on a spherical Earth, I'm actually following an arc. Think about latitudes and longitudes. They look like straight lines if you follow them, but really they are curved. And of course, this raises the interesting question, is there any such thing at all as something that is straight? If you define straight as the shortest distance between 2 points, you have to make some assumptions. The big assumption you're making is that these points aren't moving. And of course, is it true that there are any points in the universe that are stationary? And the answer is no, but we make this assumption anyway. This means that all measurements are actually based upon the assumption that there is something called straight. An assumption actually that we're willing to make and is very useful. We just have to be careful that we don't call our measurement of length, width, or height as a truth, capital T truth, because it is based on an assumption. I'll let you do the math problems. We can talk about the average velocity. For example, if I were going to take a trip to Chicago, I would certainly hope that my velocity in my driveway is not the same as my velocity in my neighborhood, which is not the same as the velocity on the main street leading up to the interstate, which is not the same as my velocity on the interstate. So I would talk about my average velocity from here to Chicago, knowing full well that there will be times where I'm traveling very, very slowly, maybe a time where I stop to grab a bite to eat or to use the bathroom or to stretch my legs, and other times where I'm hurtling down the interstate at the speed limit plus 10%, if you're like a lot of people. I've noticed, especially since COVID times, that the opportunity for, or the number of police on the interstates to keep the speed limit reasonable is way, way, way down. There's a lot of reasons for that, but people are really traveling very, very fast on interstates, sometimes a little bit faster than they're designed to handle. Again, if you're going from point P to point Q, your net displacement, it does not take into consideration how you got there, whether it was this way or a straight line. It does depend, of course, on what direction you're going. You want to indicate the direction. Otherwise, you can end up like this embarrassed football player. We can talk about graphical interpretations of velocity. If we're going from point A to point F, this line here, right here, could represent my average velocity. This would be my average velocity from point A to point D. This would be my average velocity right here from point A to point C, average velocity from A to B. And this line here, which is tangent to the curve at my starting point, would be my instantaneous velocity, my V sub I, my initial velocity at the moment that I start. Notice that you're slowing down and then you're speeding up. So the slope of this line is because most of the time I'm speeding up. The slope of this line is I'm speeding up, but then I'm slowing down. And this line here is I'm slowing down even more. The slope of the line, of course, slope, is going to be my rise over my run, which is my change in y over my change in x. And of course, if my change in y is my displacement, d, and if my change in x is my time, this is the definition of velocity. Therefore, we would say that the slope of this line, or any line on this graph, is a velocity, assuming a particular direction. So the average velocity of an object during the time interval, delta t, or change in time, is equal to the slope of the straight line joining the initial and final point, which is what I just did. The instantaneous velocity would be the slope of the line tangent to that curve at any point, if indeed it is curved. And of course, if you're having trouble finding the tangent to that curve, you can get closer and closer and closer to the actual tangent. That's where the idea of limit comes in. And then, of course, as soon as we start getting into limits, then we start getting into calculus, laying the foundation. And so we can say my velocity at any particular moment in time is equal to the derivative of my displacement, x, with respect to time t. So derivatives, this is not a calculus-based class per se, because we usually have some people in AP college physics that may not have had a lot of calculus yet, but I'll be referring to calculus a lot. And let me suggest to you strongly that since more and more each year of my students are taking the AP calculus-based physics tests, it's a good idea that you follow along in your calculus book or a calculus book or the online calculus book that I posted on Canvas as we go through these chapters. My main goal is to get you familiar with all of the physics. All right, acceleration is our second derivative. Acceleration is our derivative of velocity with respect to time. Our acceleration is defined, there's our defined, our change in velocity divided by our change in time. And so anytime you see a graph that looks like this, v over t, whatever the line is that you're drawing, this or this or this, is going to be, the slope is going to represent acceleration, because that's the rise over the run, the velocity over the time. The units are meters per second squared or meters per second. Same thing. How much does the velocity change per time? You can have a third derivative. How much does the acceleration change per time if your acceleration is variable? You can have a negative acceleration. Negative acceleration doesn't necessarily mean that the object is slowing down. For example, if you define this direction as being positive and this direction here as being negative, and you're traveling this way towards the left, and you're slowing down or speeding up, you can have you can have both a negative velocity and a negative acceleration, especially if you're speeding up. Slowing down, you'd have a deceleration or a negative acceleration. So deceleration simply means a reduction in speed. You're slowing down. Negative acceleration does not necessarily mean deceleration. Now you can expect on your first test to have a bunch of graphs like this, where I will ask you to match the graph with a definition of something that's happening, like changing velocity or constant velocity, or changing displacement or constant displacement, or variable acceleration or constant acceleration. You should be able to interpret these graphs. And of course, in order to interpret the graph, the first thing you do is you look at your labels on the axes. And then you do your y over x, rise over run. So this would be a graph of velocity over time, making this a graph of acceleration. Since you have a straight line, you have a constant acceleration. Here you would have an increasing acceleration. Motion diagrams. If you look down here at this figure, you can see here we have a car in the first block moving at a constant velocity, zero acceleration. How do you know? Well, every single one of these vectors is exactly the same length. In the second place, you have a car that has a constant acceleration, which means it's speeding up. So these velocity vectors are getting bigger and bigger. But because the acceleration is constant, the acceleration vectors have exactly the same length. And then in the third one, we have a car that has a constant acceleration in the direction opposite its velocity. So the constant acceleration is represented by vectors of exactly the same length, but going to the left, because we've designated the right as being the positive direction. Therefore, my velocity is getting smaller and smaller and smaller until eventually you stop. Now, you're never going to get a graph that looks like that, because it's impossible to go backwards in time, which is what's happening right there. So that graph is an impossibility. By the way, we'll get to two-dimensional motion in a later chapter. And one of the ways to find acceleration is to find the slope of your curve of a velocity versus time graph. But these equations right here, and right here, and right here, you're going to use over and over and over again in the first quarter in particular, and I will derive them later. I'm going to stop here, and we will finish in a few minutes, at least for me.